it after the class. Yeah. Okay. Now the definition. Once again, my name is Segun Oke, and I will be facilitating this particular course. For those of us joining us for the first time, you are welcome to this class. Last time I tried to encourage some of us that we should lay our hands on definitions and some of the theorems and see how you can prove some of them. Now, for this one, we have it to be the definition. Let's
Sir, I thought you said you want to recap a bit so that we can get from where you stopped last
No,
week.
until you watch that video, the major thing we did last time, okay, if you still want me to recap, I will do that, but it's all about definitions and the solution. First thing we did was we did something on isomorphism. We are leading to isomorphism. We try to do the linear transformation. We try to see what are the conditions to solve some of the linear transformation. And from there, we are able to move into a definition that leads us to when do we have one-to-one mapping? When do we have onto mapping? And when do we have surjective or invertible mapping? So all these things are very key. That's why I refer us to the definitions in that manual or course material. I believe all of us now, we have access to course material. So, excuse me, let's continue. Let's U and V be vector. Let U and V be vector. Be vector space. Let U and V be vector space over a field F, over a field capital F. And let T such that U map to capital V be a 1-to-1. In the video, how many of us have managed to watch the video? If you've not watched the video, I will advise you to watch the one I uploaded yesterday night. And onto linear transformation. Okay. How do we know this particular one is linear transformation, is one-on-one, one-to-one transformation? One-to-one is the sense that we normally write it this way. Okay, let me finish this definition, then I'll give us the way we write it. The T is called an isomorphism. The T is called an isomorphism between, let me shorten this. This is between U and V. So in this case now, we usually represent the isomorphic vector space in this way. We represent isomorphic in this way by saying U, a kind of approximate, you remember this sign, we represent them U isomorphic V. So we normally do that. But let me give example here. When we said one-to-one, I gave that example in the video. I said, for example, let's say you have a map V, and then you have another map. You have the domain. Remember last time I explained domain and codomain. We have it this way. Let's say we have here 1, 2, and 3 points, and then we have another 1, 2, 3. So how do I know that this is one-to-one map? Let's say we have our W codomain. Then now say T such that V2W. Now, for this one to be one-to-one, it simply means, from the word one-to-one, it simply means this is mapped to this. Let's say A, B, C, D, and this also mapped to this, and this also mapped to this. Please, don't forget that this is a virtual class. So my writing might not be that the way you want it. I'm just trying my best just to make sure you can see something. So always listen to what I'm saying, and then from there you can judge, you can write. So at this point, this line we call it T, that's where it maps. We can call this one is 1-to-1 mapping. This is 1-to-1 mapping. Now, if you now have that is, I can call this one 1-to-1 mapping because two things happen. No element from codomain map to from domain that map to codomain twice. So in case, now let's look at this other example. If I have this and I have this, let's say I have the same thing. So I still call this one V, I call this one W. So if this one mapped to this guy, this one also mapped to this guy, and this one mapped to this guy. Now, this is not one-to-one mapping because you can see that it already violates the rules that says one-to-one. At this point, you can't call this one one-to-one mapping. Please take note of that. Now, let's look at the example. Example, Roman figure 1, or example 1. Let me put it this way. Let T such that the R of 3 maps to R of 3. That is, R in space 3 also map to the real R of space 3, such that our T is in X, Y, Z is equals to X plus Y, then Z. So it simply means that now the question now says, okay, let me write the question down, finish. Then before then, I will just call your name and then you tell us whether is, remember, the question now says, is T, and they can give you something like this in the exam or in your test or whatever, and say, is T an isomorphism? Is T an isomorphism? Question mark. Then why? Is T an isomorphism? Then why? If it is isomorphism, you have to tell us. Then if not, whether you know it or not, you have to still tell us whether it's isomorphism. Then the question further says, define T inverse if it exists. Define T inverse if it exists. So then let me give us, okay, let me write the second question on this aspect so that we move on. Question 2 says, let T such that our R of 3 maps to R of 2, which is such that T of X, Y, Z is the same thing as S plus Y, then Z. The question says, is T an isomorphism? Is T an isomorphism? Now, you can see from the question 1, who can tell us in what space are we working for question 1? Anybody?
3 spaces.
3 vector spaces.
3 vector space, thank you. I believe you know the reason. Look at the power of that R. You know how raised to power n, it means in n space, but now we are talking about 3 now. It means in R3. Now, who can tell us the question 2?
From 3 to 2.
The question 2 is what?
From 3 to 2.
We can't hear you, please.
3 spaces
3
mapped
to 2.
into 2.
3?
3 spaces mapped into 2.
Okay. Okay, now let's continue. I believe we have idea of what we are doing now. So let's continue the solution now. Let's look at the solution together. For the first one, let's prove the first one. Proof. The first thing you need to assume in the first one is what? Is the first one, can we say, is it linear? Is the first one linear?
It is linear, sir.
It is.
Okay. Tell us, why is it linear?
Because if you check for the additive of the two, as in of 2 vector spaces from 1 and we map to 2, it will definitely be linear. Why? If you check for the scalar multiplication also, it is valid. It obeys law 1 and 2.
It obeys law of linearity.
Yes, sir.
Which is transformation. Then what is the second one?
So the second one is, it is isomorphic, because if you check for cat C, it is 0, which is also 1 to 1. So I think it is isomorphic. That is 1 to 1 and on to.
The third one is what to check. Now, let's solve it. We know that at this point, how do we know? Because some of us, what we are saying, we are just saying Arabic. So our T, let's start from there. So T is 1 to 1. That's the meaning of 1 to 1. That is because T is 1 to 1 because we all know we are working in the Tor space and it obeys the Tor space. S, Y, Z. Is the same thing as T of S prime, Y prime, Z prime, which implies our S, Y, Z is the same thing as S prime, Y prime, Z prime. Now, when you see T, I just try to take it out of the transformation, then it's 1 to 1. Like the example that I said the other time, that's where the first element from domain map to the first element or map to another element in codomain. So, and you can see that none of them map to two elements at the one element. Two element does not map to one element at the same time. That's what makes it 1 to 1 mapping. But in this case now, we already established that we have X, Y, Z, and it also mapped to X prime and Y prime and Z prime. So now that we've already established that, nobody will give you. Don't say that they did not give us. That's why we call it algebra. Don't say that. Please, can you please mute yourself, everybody, except if I call you. Those of us opening our sheet of paper, please mute yourself. Thank you. So you can see that you don't need to, you just have to improvise. That's why they call it algebra. It's not that they did not give us Y prime, X prime. Where does it see it? No. All you need to do, you have to prove that this theorem is okay or is not okay, either of the two. Now, the second one that we need to check is to check that T is onto, because T is onto because any SY, Y, Z, they all belongs to our R of 3. Don't forget, can be written as T into S, minus Y. Remember, Y, Z, according to our definition, sorry. So from there, we can now say, therefore, T is an isomorphism Please read the definition of isomorphism from day one. We said that for us to have isomorphism, our T, you must be able to establish that it is 1 to 1. You must be on to linear transformation. And the third one, anyone that can obey the two laws is automatically what? It will give us the isomorphism. But now, there is a particular question we're given that we need to quickly solve that says T. Therefore, we should define, therefore, T inverse is such that R of 3 leads to map to 3 exists. We want to establish this. It exists. and divine, and is defined by T inverse into S, Y, Z, which is the same thing as, which is mapped to X minus Y, Y, Z. So for this case now, it is simple that from our definition, we already established this. Remember the definitions of this particular one. So all these definitions will guide us, like I said, and you will be able to appreciate what I'm saying here. If you watch the last minute video that I uploaded, please do yourself a favor, because I know the time will not permit us. That is why I quickly upload that video for our own use. Remember, as I said, I'm just to come to the class and ask 1 or 2 questions just to facilitate. But I didn't fit that. No, it will not worth it if I come here and facilitate and I know my students are still nowhere to be found. But the second question says, we have this question, let T such that R of 3 tends to map to R of 2. I will ask you this question. Is this question, number one, is it an isomorphism? No, because it's not an isomorphism, because T is not 1-to-1. Don't forget. That is, T is not 1. You have to obey the law. If you don't obey that definitions, there's nothing you can do. T is not 1-to-1. Then, since T is not 1-to-1, I can now say that we can say T is not 1-to-1, since 1-to-1, 1 belongs to, like the definition one of us told us now, is of kernel of T, belongs to kernel of T. So we need to check that, and we need to be satisfied with that. So I hope I'm clear. Any question? So if you have any question, please consult your books, and you can also reach me. Now, let's look at another example. So this, as I said, this course is not that hard the way you think. All you need to do is just to make sure you know the definition well. So let T such that R of 3 tends map to R of 3 be defined by T in bracket x1, x2, s3, which is equals to same thing as x1 plus s2, s3, s2 plus s3, then s1 plus s2. So we want to say this, and the question says, is T invertible? They can ask us some of these simple questions. All you need to do is just to show. Then, if yes, find a rule for T inverse find a rule for T inverse, like the one which defines our T. So the first thing we need to do here in this case is just to also prove, and while you are trying to prove, don't forget, we are still on linear transformation. T is a linear transformation. You have to establish that. Then how do we establish what is invertible? The definition is in your course material. Please go and check it. Then is the same thing as when we are talking about onto. So please watch the video, as I said, and for those of us that have watched the video, you understand what I'm saying. If not, you can also consult your course material. Now, number one, establish is T is what? Transformation, linear transformation. T is a LT. LT means linear transformation. Now, we can now establish LT means linear transformation. We can now go ahead by saying if X, Y, Z belongs to kernel of T, then our T of S, Y, Z. We know the definition of kernel of T, which is equals to what? 0 is equals to 0, 0, 0. So therefore, we can establish that X plus Y is equals to 0, which is equals to Y plus Z equals to X plus Z. Remember the way we are trying to map them together, and everything implies that our X is equals to 0, which is equals to Y and equals to Z. Now, don't forget, what this thing is saying is very simple. Back to the definition. I've told you, go and learn all these definitions. They are very important to us and to yourself. The question is very simple. All you need to show is just 2 or 3 lines, then you have your full mark and you go. The first thing says you need to establish is kernel. We know the definition for kernel. Know the definition for kernel, know the definition for invertible, know the definition for one-to-one, know the definition for onto. So when you map all these things together, we can then implies that our kernel of T is this equals to 0, 0, 0, which implies our T is 1 to 1. So 1 to 1, our T in this case is 1 to 1. Then by the theorem above that I've mentioned about the invertible, we can conclude at this point that the T we are working towards in this case is invertible. The T I'm talking about, excuse me, is invertible. Now, for us to define, you can conclude in your notes, you know the theorem. Please, I know the material might not be interesting, like some of us complain, but take your time and write them out, some of those things, then you will enjoy it. Now, let's define, to define the T inverse such that the R3 maps to R3, suppose now we have suppose our T inverse is X, Y, Z. Now, remember I told you, you improvise. Nobody will give you this. A, B, C. Since I know that I'm working in the 3-dimensional, it will map automatically to 3. I have to, some people can call their own XYZ. We have XYZ, you can call this one A1, A2, A3, anything you like that you know you can cope with. Then nobody will wrong you. Then our T into A, B, C is the same thing as S, Y, Z. Meaning the same thing we did the other time is going to imply that we have A plus B, B plus C, and A plus C. So, which we also map go to S, Y, Z. So then we can proceed by saying from here implies to A plus B is equals to X, B plus C is equals to Y, and A plus C is equals to Z. From here, then from here, it's still the same thing. You can see what we are doing. So I believe from here, you should be able to finish everything. Please complete it and get me the final answer. So I will give us the final answer. Then I want you to do yourself a favor by T inverse of S, Y, Z is the same thing as S plus Z minus Y over 2, S plus Y minus Z over 2, then Y plus Z minus S over 2. Everything for any S, Y, Z that belongs to the R3. I want you to complete this to this. This is the final answer. Then on your own, go and finish this. I only jumped 2 lines here, and I want you to do it. So that's one of the things I want you to lay your hands on. It's for your own good, and it will help you without any doubts. So let's look at the theorem, and we'll look at the theorems, because I can see from some of your works that they will give you a theorem, they will ask you to prove and show a particular thing. Somebody was asking the question last time that, but is it not going to be, is it OBJ or whatever you asked the question? Now, it all depends.
Excuse, sir.
Yes.
Excuse, sir.
Go ahead.
We didn't finish writing the assignment, sir.
Oh, sorry. Are you okay with this?
Yes, sir. Yes, it's okay, sir. Thank you.
Okay. You're welcome. So some of us are asking, the question will not be, it's not that hard. As a matter of fact, you just have to study your course material. They are very simple things. All you need to do is just to be dedicated and devoted on this aspect. And let me prove this theorem, then we check some of those things. Then if you have any other question, then we'll call it a day. Sorry for taking some of your time due to the technical, and I have to meet up with you. So by next class, we'll be talking about vector space that will lead us to matrices, which we need your 100% attendance. And somebody complaining, Ola Deborah, I really don't understand. Yes. It is best if all the students turn off their videos, okay? They are distracting. Please turn off yours. You said they are distracting you, right? Or they are affecting your network too. Please, can we just be our brothers and sisters keeper? Just off your video. All you need to do is just watch my own video, which I'm sharing. Yeah, the video is on YouTube, but it's on your coursework, on your course page rather. If you check your course page, you will see the video there. So is codomi as same as range? Codomi is, look at for those of us that are in class last week, I tried to define the codomi and domain for us. Please look at that video and check what the course material. Please, is the second diagram onto mapping? No. No, but it's only that we call it not one-to-one. They are not opposite. They are not one and opposite. Yes, I've told you, they said the writing is not clear on the screen. That's why I said, but it's manageable. All you need to do, remember, I'm not using perfect board, so please don't expect perfect writing. As I'm talking, please be writing if you want to write. It's not compulsory, but I think it's necessary. So by the time you are in class and I drop the video again, I think, excuse me, it will go a long way for us. So please, that is what the COVID has taught us. Let's try as much as possible to adjust. Now let's look at this theorem. I can call this one theorem 1 or theorem 10 or anyhow. Let T such that U map to V, U map to V be a linear. Let me just use LT so that I won't be writing too much, so that some of us will not be complaining. Be a linear transformation. Be a linear transformation where U dot V are of the same finite dimension, same finite dimension, of the finite dimension. So then the following, in the short form, the following statement are equivalent. The following statements are equivalent. A, T is 1 to 1. B, T is onto. C, T is an isomorphism. So for us to prove this, because we'll be referring to this particular theorem in due course, let's look at the proof. Then the proof says, to prove the results, we will prove that first, our A is equivalent to B and is equivalent to C. Then also equivalent to A. C also equivalent to A. So we can now say that let dimension U equals to dimension V equals to N. I gave us definition, this particular definition last week or in our last video. For those of us that are joining us, please do yourself a favor by listening to watch those the videos. I think it will help us. Now, A implies that the kernel T is equals to 0. From our previous theorem that I've already proved with us on the kernel and the new T. Hey, excuse me. Hence, the new T of T is equals to 0. Therefore, by the previous theorem that says the rank, remember, by the previous theorem that we've proved or we've shown ourselves and definitions, that says that the rank T is equals to N. That is, our D, which is dimension rank T, is also equals to N, which is equals to the dimension V. But arm of T is a subspace of V. So at this point now, if arm of V is the subspace of V, then we have this. We can now say R of T is equals to V. That is, our T is onto. Our T is onto. If we can show that T is onto, that is, if T is onto, it simply means that our B is true. So A is equivalent to B. A is equivalent to B. Similarly, if our B hold, similarly, if B holds, then rank of T is equals to N. And hence, the new T of T is equals to 0. Then we can also prove this consequently. Remember the definition of new T, the rank. We are just applying the definition here. We are not doing anything spectacular. We are just going front and back from our definitions. And that is why I said, let that definition be part of you. Consequently, we know that kernel T is defined as 0, right? The set 0, and T is 1 to 1. Hence, T is 1 to 1 and onto. That is, our T in this case is isomorphism. Our T in this case is isomorphism. Therefore, B implies C. And it will also follow immediately. A also follow the same thing in order to map the according to the definition. So I just want to encourage us to lay our hands on some of those things. I will give us one example, then we call it a day, or we call it a week rather. So example. Example. Let's T such that V over W maps to V over U, such that our T in bracket V is equals to T positive is equals to T of this V plus U. Don't forget what you need to show. The question now says, A, check that T is well defined. B, proof that T is a linear transformation. Then C, what are the space then T and RT in question? So this is very simple things that we can lay our hands on. For us to establish that T is well defined, it is very simple. So, proof. To prove this, we have our V plus W from here. So V plus W is the same thing as, let V plus W will now be equals to V prime plus W, which implies we have V minus V prime. Everything belongs to that W, which also contain in our U. Now, what we are saying is, remember we improvise the other side. Then by the time you match them together, they all belong to that W. And they also contain in the capital U that we are working with. So if it is the same thing like that, I can boldly say that from here implies V minus V prime contain or belongs to U, implies U, V plus U is the same thing as V1, V to U, which implies that T, the transformation of V plus W, is the same thing as T in brackets V prime plus W. So what we are trying to show here is like we are moving from one point to the other. Look at the definition from V plus W up equals to V prime plus W. But we try to establish that. We establish this particular one by saying, we try to establish this particular one that truly they all belongs to the same U that we are working with. So that is why we have a cover to be able to define the transformation we are working towards. So then we can conclude at this point, because they can give you, is the T well defined? Then you can only show them in this case, which implies that, or we can say, therefore, our T is well defined. That's the solution. Then we can move on. B, our B says, prove that T is LT. We all know the LT, we all know the conditions of the LT, and it is very simple by saying for any V plus W, V prime plus W in V divided by W, and don't forget the multiplication scalar, and the scalar A comma B we have it to be our T in brackets A, all in brackets, V plus W, then plus B into V prime W is the same thing, or is equals to T in brackets AV, if you open the brackets, BV prime plus W. Then we all know that W also they contain in U. So you agree with me if I said AV plus BV prime plus U. So then I can now establish that, which implies A into V plus U plus B into V prime plus U. As we all know that they all contain, which equals to A. Now, if I want to write this in transformation, V plus W plus B, T equals to V prime plus W. Therefore, based on the definition of the linear transformation, our T is a linear transformation. We already established, we already bring out our scalar and make it in this format. Then lastly, we are to show that the curve, we know the definition for that, and I think I will ask us to go and solve it on our own. But let me just help us by saying the kernel T is the same thing as, in this case, V plus W, such that V plus U is the same thing as capital U, since U is the zero. Remember the definition of kernel of T for V over U. So I think we can solve it, or I should just write the last line that is there that says V plus W such that small v belongs to the U, which is the same thing as U all over W. So then our definition for RT will be RT is the same thing as V plus U. Then we have small v belongs to capital V. It's the same thing as V over U. So these are the things we are trying to sort out. Then I will advise you, please, some of the exercise that is in our course material, please try as much as possible. I use some of them also as an example. Yeah, somebody asked a question, can we, please, that the way you have been interchanging you, don't let it confuse you, please. You can also design your own alphabet or design your own letters you want to be using. I only use, somebody said the way you are using U and W. Please, what you need to do is just understand the concept. Don't memorize this U, V, W, no. You can design your own the way you can understand it. Nobody will penalize you for that. Please take note of that. Then, sir, reading the course material, can we understand it step by step of linear? I don't know. It depends on the individual. It all depends on individual. So let me stop sharing. Are we together?
Yes, sir. Please, I just want to copy.
Yes, sir.
Can I stop sharing, or some of us are
No,
still
sir.
writing?
Yeah, yes, sir. I'm still writing.
Okay, please quickly copy. Now, so what I'm trying to say is for course material, this is not English. And remember, there is always difference between lecturer and the textbook. You can have the textbook. We all have access to course material. Nobody is hiding it from you. But some of us are since the time you've been taking the course material, do you really understand what they are saying?
No, sir.
So, except if you would break it down like this for ourselves and explain what's transfer between one step, step A and step B. It happens to me too, some years back when I was introduced to this particular class. And I got to know that, okay, I have to do linear algebra. And some of us in mathematics, welcome to the world. You see, when you're in mathematics, you have a lot to learn. You do linear algebra, you do abstract algebra. It's not because we are scaring you, it's because that's the course requirement. And that's the degree requirement. So can I stop sharing now?
Yes, sir.
Okay. So that is the course requirement. And I want us to also know that you are not the first person to do something like this. We are all in together. If I can do it and I survive it, then you can survive. I believe so. So it's all about dedication. It's all about time. It's all about you yourself. Find time to do the needful. Just out of your own schedule in a day. Just check the what is there, especially in the course material, and see whether you understand or not. Just try and read it. And I always tell people the best way to learn is to write it out. Let me stop recording. We can't hear your question, please.
Okay, I will come again, sir.
Just try as you can say the chat.
Can you hear me, sir, now?
Yes, I can hear you.
Okay, sir, I will do that, sir. So can I ask the question now?
Go ahead.
Okay, my question is on rank nullity that states that the dimension of our domain is equals to dimension of our ket and rank. But I'm not understanding that particular theorem. And the second question is it applicable to the inverse of linear transformation also?
Now, what I will say in that case is this. At your level, what you need to do is to understand, is to believe in the definition. We are not going to prove the definition. We are not going to, it's just a definition. Are you getting it? And the properties. Yes, so if you can follow the definitions that says that, you don't need to bother your head about how do they come about the definition. If I want to ask you, for example, let me give you a scenario. How did they come up about A, B, C, D? Some of us, we don't know. They just taught us that it's A, this is A, and you agree it's A for this particular level. A time will come for those of us that are doing mathematics, we go into real establishment. But as for you, you are just here to apply it and move. So what I would advise majority of us